let's discuss this theorem. So what we have a X as a matrix space and A is subset of X. Okay, and what we have to prove? We have to prove if and only if is there. That means we have to assume first part, we have to prove second part. After that we will assume second part, we will prove the first part. Okay, what we have to prove? A is open if and only if A is equal to A interior. This thing we have to prove. Okay, so I have written the basic things. So we will start with, we will assume that A is an open set and we will prove that A is equal to A interior. So assume that, first I write, assume that A is open, and what we have to prove? To prove that A is equal to A interior. Okay, so see how to prove two sets are equal. We prove one set is subset of second. After that we prove second set is subset of first. Then we can declare both of them are equal, right? See, one thing is obvious. By definition of A interior, A interior is subset of A. This thing is obvious because in definition of A interior, we take points, interior points, right? Interior points, that means first we take point from A and then we check it is interior or not. That means points are taken from set A. So obviously A interior is subset of A. So now to prove that A is subset of A interior, we have to prove reverse part. That means I have to prove A is subset of A interior. How to prove one set is subset of other? We take one arbitrary point from A, and we will prove that it is in A interior. Let X belongs to A. See, but one thing we have, that is A is open, but A is open. So definition of open set says there exist R greater than 0 such that Bx are subset of A. Okay, A is open, so that's why we can find open ball around X which entirely lies inside A. But see, this is definition of interior point also. So therefore we can declare X is an interior point of A. In definition of interior point also we do the same thing. In interior point, how to prove X is interior point? If it is possible to draw ball around X which entirely lies inside set A. So here it is possible. So that's why we can declare X is a interior point of A. That means X belongs to A interior. So therefore, basically we had taken X from A and we proved that it is in interior of A. So therefore we can declare, what can we declare? Therefore A is subset of A interior. This is equation number 2. In equation 1 we say A interior is subset of A. In equation 2 we say A is subset of A interior. So therefore from 1 and 2 we can write A is equal to A interior. So in this way we have proved the first part. We assume A is an open set, we proved that A is equal to A interiors. So now converse part is remaining. In converse part we will assume A is equal to A interior and we will prove that A is open. Make a screenshot of it. See, in converse part we assume that A is equal to A interior and what we have to prove? A is an open set. Okay. See, we know that, I will mention here, we know that A interior is an open set. I will mention here proof is required. Okay, proof is required. That means you're supposed to prove this part here. But see, in our previous video we have already proved A interior is an open set. So that's why I'm avoiding it. Okay, actually if it is asked as a separate question, we supposed to prove here. But if there are A, B, C such statements are there, and in first part already we have proved A interior is an open set, then simply we can write from A we can write this. Okay, So A interior is an open set. This is a basic thing we have, and A interior and A, both of them are equal. If this set is open, this set is also open. So therefore A is open, since both of them are is open. Okay, because A is equal to A interior. So in this way we proved A is an open set. Okay, so in this way we have completed this theorem. So we'll stop here. Thank you. Bye bye.